All right, welcome back, class. We're going to pick up this week with rational functions. So I'm going to go through a couple of the parameters. There are four main concepts when breaking down a rational function. You'll have to find the x-intercepts, the y-intercepts, and the vertical and the horizontal asymptotes. So the function will give away what these parts are based on the types of factors that you'll see in the structure of the function in the numerator and the denominator. So we're going to go through that right now and just identify each of the components and try to lay it out pretty straightforward for you. All right, so the first one we'll deal with are the x-intercepts right here. How do you identify x-intercepts in a rational function? Now, a rational function by definition is any function that is set up in like a fractional form. A rational number is any number that can be expressed as p over q. So a rational function, if we write it over here, any rational function can be expressed as f of x is equal to some p of x over q of x, some function over another function. So if you notice that any kind of fractional setup is considered a rational function for these cases. So for the x-intercepts, we're going to look at a couple of examples here. I have my calculator out for each of the three of these. Okay, I have the three plugged in there. So what I'm going to do is just plug in, and we're going to go up to the top one right here. I'm going to turn the other two off temporarily just for a second, so we'll get to those in a minute. All right, so here's the first graph. If I hit zoom 6, zoom standard, we take a look at the picture, and we're looking for the x-intercept. So it looks like it crosses the x-axis somewhere over here. So if we want to go find that, you could easily hunt out for where that is. It looks like it occurs right about there. That's where it hits the x-axis, 2, 0. So if we go back to the equation, we look at the equation, what gives us away that value? Well, we know that 2, 0, the x-intercept, in this case would be x equals 2, so that yields 2, 0. So we're going to identify, well, what part of the function gives us that each time. So if I turn this one off and go to the second one, and we go back to the graph. So now I have the second one turned on. So we're going to graph the second equation. Here's the picture for the second one. You'll notice that there's no x-intercept over here. It looks like there's an asymptote horizontally, but it crosses the x-axis over here. So where is that? Again, we can check the table of values. And, oh, there it is. It's right there at -3, 0. So this one, again, has an x-intercept at x equals -3, which would be -3, 0. And then if we go to the last one, let's go to the y equals. Again, I'm just going to turn the second equation off, and I'm going to turn the third equation on. So there's the equation. We look at the picture, and notice there's a little bit more to this because it has more factors in the equation itself. But it definitely looks like it hits the x-axis somewhere in two different spots, right? One on the negative side, one on the positive side. So if we go to the table of values, rather, we can see right away we were right at 1. There's one of the x-intercepts at -4, 0. The other x-intercept was on the positive side. Nope, there it is. It's at 3, 0. So if we write those out, this one was at x equals 3 and at x equals -4, which meant we had one at 3, 0, and the other one was at -4, 0. So we verified it on the calculator. It says, in general, what part of the rational function will identify all of that? So clearly you can see it's the factors of the numerator you want to set equal to 0 and solve. That will identify your x-intercepts. Okay, and then we go to the second equation, or the second question down here, rather. It says, how can you determine where the x-intercepts are using the table of values on the calculator? Well, if you notice what I was doing before, we were looking for where, go to the table of values where y is equal to 0. So when you look at where the y equals 0 is, you can find the x-intercepts as long as they're integers. And remember, your table of values is set up for integer increments. If it's an integer value, you'll be able to see it on the table of values. If it's a fractional value, you will not be able to see that x-intercept on the table of values. You'll have to do a second trace intersect with the x-axis in order to find it in those cases. All right. So now we go down to the bottom. And we have a more generalized version. Okay, well, what if you have this kind of abstract equation, y equals x plus a over x minus b? Can we use the same concepts to figure out what would be the x-intercept in that case? Kind of hard to use a calculator here, but now that we know that we can use our x-intercepts, we can say, oh, well, the numerator factors, right, if we go back to what we said on top, set the numerator factors equal to 0. So if we do that, we can just write out x plus a has to equal 0. And if we solve that out, we get x is equal to negative a, which means negative a comma 0 would be your x-intercept in that case. And I'll try to color code these. I'm going to use green for the x-intercepts and some other colors for the other parts as we go through them. So that way when you get to the example for you to try on your own, you can maybe utilize the same types of highlighter colors if you have them. Okay? So x-intercepts, the summary is, take the numerator and set it equal to 0 to solve. That'll give you the x-intercepts. Okay? All right, the next one we try now are the y-intercepts. So how are we going to figure out these y-intercepts? Well, let's do the same thing. All right, we're going to use the calculator, and I'm going to use the same equations on the calculator. I'm going to type them in. I know the first one is a little bit different. This one is x minus 6 over x plus 3. So I'm just changing that on my calculator now. So I have that there. So I want to find the y-intercept, right? So that's where it crosses the y-axis. So I have that equation, the first one typed in. If I hit the zoom standard graph as the same settings I have, looks like the y-intercept is right down here in the negative region. So if we go to second trace, you can check the table of values. There it is right there, 0 comma negative 2. So that lines up with what we're seeing here. So this one has a y-intercept of y equals negative 2, which means 0 comma negative 2. If we go to the second equation, that one is x plus 3 over x minus 1. Let's turn this one off and let's turn that one on. All right, so I have my second equation. Let's hit the graph key. Y-intercept looks like it crosses somewhere over here. So it's in that negative range. Again, let's check the table of values. And sure enough, 0 comma negative 3 is right there. So we go there. There's our 0 comma negative 3. So y is equal to negative 3, which is 0 comma negative 3. We go to the last one, and we check that. Let's just turn this second one off. We'll put the first one on. And I have the graph. So this is going to have more pieces to it, if you will. There's more factors, so that generates more breaks in the graph, you'll see. So the y-intercept is somewhere around here. We have to figure out where it is exactly. So if we go to the table of values, again, there's your equation, 12 over 35. So that's not an integer value. So y is equal to 12 over 35, or 0 comma 12 35ths. So there's our y-intercept values. Now this might be a little bit more abstract to find initially. So while we're going through it, it says in general, how would you determine what the y-intercept is? Can there be more than one? Well, that's an easy question to answer at the beginning. You can't have more than one y-intercept because in that case, you'd have more than 1 point for the same x value. You'd have more than one output, and therefore it would fail the vertical line test. So this answer is an easy answer right here. No, because it would fail the vertical line test. So therefore, it wouldn't even be a function in that case. And whoops, let me just enlarge that. Sorry, guys. All right, so it would fail the vertical line test. So there can only be one y-intercept for any function, obviously. All right, now how do we determine that from the equation itself? What would give away what the y-intercept is? So this one turned out to be negative 2. This one turned out to be negative 3. And we're looking at the structure of those equations. This one's a little bit tougher to determine. But if we go through, I'm going to use the pink highlighter for this one. If you notice, if you look at the constant terms here and here, negative 6 over 3 is negative 2. Positive 3 over negative 1 is negative 3. So those two worked out. This one's a little tougher. But if you look at negative 3 times 4, that's negative 12. Negative 5 times 7, that's negative 35. Negative 12 over negative 35 is 12 35ths. So in general, how are we going to find out what that y-intercept is? What we can use is find the ratio of the constant terms in the numerator and the denominator. So if you look at the constants, now it would be easier if we were to distribute this, because if you distribute the top, notice you get x squared plus x minus 12 over x squared plus 2x minus 35. So if that's me double distributing this whole thing, I get that. And if you look, you would see the constant here and the constant there. So the ratio of the constants is actually the y-intercept. You can also just simply set x equal to 0 and solve for y. You can do that too. If you plug in a 0 here, here, there, and there, you'll get the same 12 over 35. Plug in a 0 here and here, you get 3 over negative 1. Plug in a 0 here and here, you get negative 6 over 3. So this would also be a viable way to do it. But if it's already in distributive form, you can just look at the ratio of the constants. All right, now we on the calculator found it a little bit simpler. Just go to the table of values at x equals 0. Find the y. That's all you really have to do is find the y value at x equals 0, which is the same as doing this. Setting x equals 0, you find the y. That's the y-intercept. So in general, when we go to this bottom question in a more abstract form, you have x plus a over x minus b. One way to look at this is to just take, the ratio of the constants. So here you would have y equals a over negative b, which would mean 0 comma negative a over b. You could also plug in 0 for x and you would get a over negative b, same answer. Okay, so that's in more abstract form. So the ratio of the constants will be the y-intercept. All right. Okay, moving on to the next. We have 2 more pieces. Now we're up to vertical asymptotes. So let's get this set up. Page 3. How do we find the vertical asymptotes for a rational function? All right, well, the vertical asymptotes, again, I'm going to set the calculator up again. And in the first equation, this one changed back. This is x minus 2 over x minus 5. All right, so I'm just going to turn off the third equation so I don't have all of them on. So I've got the first equation on here. Zoom standard is set up. And I'm looking for the vertical asymptote. That's that vertical line that breaks the graph apart. So it looks like it's somewhere over here. If I were to draw an imaginary dotted line right through this spot right here. So where is that spot exactly? Well, it's hard to tell if you count the tick marks along the x-axis, and maybe it doesn't happen at an integer value, but in this case, let's look. I'm going to look for somewhere on the positive side around 5 or 6. Oh, something interesting happens right there at x equals 5. At x equals 5, the function is not definable. There's no output, which is why the graph snaps apart. So over here at x equals 5, that's that vertical line that I get where the graph breaks apart. We look the same thing for the others, and we turn the first equation off. We'll turn the second one on. All right, I hit the graph key. So now I'm looking again, where does the graph break apart? It looks like there's this imaginary vertical boundary line right here, that vertical asymptote. Looks like around 1. Let's check the table of values. And sure enough, if you look, there's that same special property that happens there. So at x equals 1, this graph breaks apart. There's a vertical asymptote. What happens when there's multiple factors? Well, let's turn this next one on. All right, so I've got the next equation on. The last one that's got multiple factors in it. You may notice that the more factors you have, especially where it determines the vertical asymptotes, we have more breaks in the graph. There's one back here in the negative section, and then there's one over here in the positive section. Let's go see if we can find out where they are. In the negative section, oh, there it is. It happens at x equals negative 7, which would make sense over here. That's negative 7, 8, 9, 10. And then again, back at the table of values, on the positive side, there it is right there. So at x equals positive 5, again, 1, 2, 3, 4, 5, right there is where we were expecting it. So in that table of values, you can see what's interesting there. So here, this one had one at x equals 5 and at x equals -7, had two vertical asymptotes. So in general, what is giving away this part of the puzzle, if you will, right? So I'm going to use the orange highlighter for this. If you look at the factor in the denominator there, and then look at the answer for the vertical asymptote, and here as well, and both of these as well, you can see that the denominator factors are what indicates the vertical asymptotes. So in this case, we're going to set the denominator factors equal to 0 and solve. That's going to indicate the vertical asymptotes. Just like when we did the x-intercepts, it was the numerator factors equal to 0. For the vertical asymptotes, where it's undefined, it's where the bottom is 0, so it's going to be where the denominator factors equal 0. How can you determine the vertical asymptotes using the table of values? That's that next question down here. So just like we were doing in the beginning examples, all you have to do is look for the error that occurs on the table of values. All right, so where you see that error, but again, same warning as previously, this only works on the table of values if you have integer answers for these. Obviously, if they're not integer answers, you may not see them appear on the table of values. They might be in between integers at fractional values, okay? So then we go to the more abstract answer. So we've got this y equals x plus a times x minus b over x plus c times x minus d. But we know that we only care about the denominator factors being equal to 0 when we're talking about vertical asymptotes. So in this case, we can set up a little t-chart. As long as x plus c equals 0 or x minus d equals 0, then we know we have vertical asymptotes because it'll be undefined. So here, x is equal to -c and x is equal to d. And remember that vertical asymptotes are vertical equations of lines. So they're always going to be x equals some constant. X equals a number for those vertical asymptotes. All right. And now we're up to the last one, which has the most possibilities to it, I guess, if you will. So the horizontal asymptote, something we actually did earlier in the year when we were talking about limits as x goes to infinity. This is an example of like long run behavior. What happens to the function, in this case, a rational function, as you go out in really far directions in both the positive x value and the negative x value? So as you go to x goes to positive infinity, so we're talking about for end run behavior, the limit as x approaches positive infinity or the limit as x approaches negative infinity. So these would be examples as you go far to the right or you go far to the left, what's happening to the graph, where is it approaching? All right, so I'll speed it up a little bit with the calculator and I'll save you some time. If I were to plug this into y1 and look at where the horizontal line is, I'm going to notice that it starts to level off as you go pretty far out around y equals 3. It's that horizontal line that it's going to start approaching. If I plug the second equation in, you're going to notice that it looks like the function approaches the x-axis really far to the right and to the left. It looks like it's almost curling right at the x-axis. So this is going to be a y equals 0 horizontal asymptote. And then this one's a little tougher. When you look at it, it appears that it's just above the x-axis. It turns out to be y equal 1. So how do we know where those answers are going to come from? When you graph these out and you search it out really far and you start to see where the graph starts tending towards. If I were to do one example for you, I'll use the last example in this case, which is the more complicated one. So I have that in there. That's in y3 right now. So we're going to do, how do we know that it's y equal 1? So here's the equation for the third example. And I'm going to hit zoom standard to start. But that's not really the window I want to look at because, again, remember, we're talking about really far values of x, like the end run behavior. And this is like the short-term behavior. I want to find out what's going on really far out. So your window from -10 to 10 in the x direction isn't really big enough. I want to expand this really far. But if you start doing that, then you lose the scope on the graph itself. And it's kind of hard to see. So what you can do is change the table of values. And instead of starting at 0 and then checking the table of values, because that's not really long run behavior, all these values. What I want to see is what happens as we start going to far values of x. So I'm going to go to the table setup, and I'm not going to start at 0, but I'm going to start really far out to the right. So I usually use 1,000,000. So there's 3 zeros and 6 zeros. You can't see them, but they're in there. I go back to the table of values. And if you notice, you'll start to see all the y values approaching the same number. So this is over at 1,000,000 and beyond. And I could do the same thing for negative 1,000,000. You'd start to see the same things. If you notice, that's the asymptote that we're approaching. It doesn't actually hit that number, but the calculator is approximating it. So you can use your calculator to approximate the long run behavior if you just change your table setup to start at a really large value of x. And then it will give away approximately what the horizontal asymptote could be. But there's an easier way to do this. We've done it before in class. If you look at the structure of the equations. So the easier way to find the horizontal asymptote, so I'm going to abbreviate, the horizontal asymptote is always a horizontal line, if there is one that exists, and it comes from y equals the leading term of the numerator, and that's divided by the leading term of the denominator. So we've done this in the past where we've looked at long run behavior when we did limits as x approach infinity. We took the leading term of the top and the leading term of the bottom, and then you find out what that reduces down to. So you can use the calculator. I don't really recommend it too much, but you could. And the way you would do that is set the table of values to begin at 1,000,000. Oops. And see what the y value is. It'll approximate the horizontal asymptote for you at that point. So that's one way to do it, but that's a lot of manipulation with the table. And then you always have to remember to change the table setup back again if you want to do some other investigation in the short run behavior. So I'm not really a big fan of that. It's usually easy enough to take the leading terms of the top and bottom. So we take an example over here for these, and we've got 2 times x times x. If we were to distribute all of this out, this is going to turn out to be 2x squared plus a lot of other stuff over 5 times x times x. This will be 5x squared plus a lot of other stuff. But it doesn't really matter what the other stuff is because it's only the leading terms that actually matter for the top and the bottom. So when you distribute that, you get 2x squared over 5x squared. Or in other words, when we reduce this down, this is going to come down to y equals 2/5. That would be your horizontal asymptote. This would be very hard to see on the graph because it's not even an integer value. You could use the table setup method and just set your table really far, and you'll see 2/5 on your outputs. But it's a lot easier to just distribute out the leading terms. Okay, now there are 3 different cases of what can happen with asymptotes or end-run behavior, if you will. So one of the cases, I'm going to use the function y equals p of x over q of x to define my rational function. So the numerator function is p of x, the denominator is q of x. So that would be like the top of this is p of x, the denominator would be q of x, and I'm going to define it based on those cases. So case number 1 would be if the degree of p of x is smaller than that of q of x. So if the degree of the top is smaller than the bottom. Okay, now we saw that actually in the example, and just scroll back up here. Here's an example where if I highlight, the degree of the top was a first degree, the degree of the bottom was a second degree. And if you notice, it approached 0. Now here's the reason why that happens. Okay, if the degree is bigger on the bottom, then the bottom's always going to outgrow the top, and it'll approach 0 for large values. So you'll get y equals some constant over x. And again, as x approaches really large values, right, then this will approach 0 every time because this is getting infinitely large while that's staying the same. So in this case, if the degree is bigger on the bottom, then you're always going to have y equals 0 as your horizontal asymptote. So that's always going to be the case if the degree is bigger on the bottom than it is on the top. All right. Then we have case number 2. If the degree of p of x is exactly the same as q of x. Okay, so then what we get is an example like that would be an example in our model right above it. 2 times x was 2x squared. On the bottom was 5 times x, came out to be 5x squared. Second degree on top, second degree on bottom. So if you notice, they just canceled out. So in that last case, if the degrees were the same, then the horizontal asymptote turns out to be just the reduced form, which is y equals the leading term of the top over the leading term of the bottom. And it's just going to end up being coefficients because all the variables will cancel out. So whatever the coefficients turn out to be, like in this case it was 2 over 5, end up being 2 over 5 here, horizontal asymptote. So your leading terms, all the variables will cancel out. All right, and then in case 3, this is the toughest one, but luckily we won't see too much of this for this year. If the degree of p of x is bigger than that of q of x, that means the degree is bigger on top. So this is a little unusual. I could give you an example. If you had y equals x squared over x to the first. If we reduce those terms, so remember, and it doesn't matter if there were other terms here, as long as they're lesser degrees. So we have the leading terms highlighted. If you notice, this turns out to be y equals x over 1. As x approaches infinity, if the numerator has a power of x in it left and the denominator doesn't, the numerator is going to outgrow the denominator. It's going to take off to infinity. So what ends up happening in the graph is it starts taking off and getting bigger and bigger and bigger. So in those cases, we actually don't get a horizontal asymptote at all. So we say there is no horizontal asymptote. Those cases, we have what we call like a slant asymptote or an oblique asymptote, but you wouldn't actually have to find out what those are in those cases. So in this case, if they just said if the degree is bigger on top than it is on bottom, what is the horizontal asymptote? The answer is there is no horizontal asymptote. It's a slant asymptote or an oblique asymptote, so therefore there is no horizontal leveling off of the graph. Okay. So the last question is where it says putting it all together on the last page. I'll turn the video off now if you want to give that one a shot, and then I'll have the answer key posted for you for tomorrow. Okay, good luck, guys. And I'll be at my Zoom session. If you have any questions, we can definitely go over all of this.